The next talk will be by Roby.
So thanks, and thanks also to Sanjoy for this great exposition, because then I can zoom through the first few slides. And let me say that this is a joint work with Amir Abdallah, Alex Andoni, and Ravi Kahn, who I've seen yesterday, so maybe here. Oh yeah, over there. If you have good questions, then ask me during the talk. If it's like difficult question, then you should ask Ravi. Thanks. And this is like a somewhat older paper, right, in the current, I don't know, Twitter kind of like era, 2014. But I just put it here just so in case you're going to look for this work or something for details. Okay. So we're talking about the same problem, near neighbors question. I'm going to use, I'm not going to repeat the definition. I'm just going to use P for the set of points of the data, N for the number of points, and D, which was in Sanjoy's talk, was P, little p, right, for the dimension. Or actually, it's going to be like the ambient dimension. Okay, and still Q stands for query. Okay, and you want to find like the closest point, which we are going to usually denote by P star among all the points. Little p, P star is the optimal point. Okay, so let me skip this. We're going to talk about, in general, there could be different distances, but I'm going to talk about Euclidean spaces. Okay, so it's known that there is generally a curse of dimensionality. This is like a different problem, as Sanjoy mentioned. So really the issue is that this large dimension, D. And it's really like, particular when it's the ambient dimension, you may hope that somehow the dimension is D, but somehow the data has more structure. It's not worst case or adversarial configuration, and you want to leverage that information. All right, so this is the definition of C approximate nearest neighbor search, right? The same C that Sanjoy had, and you want to find any point, which I'm going to use P prime, which is almost as good as the optimal point P star. Okay, good. So usually in near neighbor search algorithms, and I'm going to talk about the algorithmic aspect of like designing fast or good algorithms. So most algorithms actually talk about space partitions one way or another. So in low dimension, there's a lot of work, and it's just like partial list of results. They're very different in a sense. Space partitions are used in low dimensions and in high dimensions. For example, in low dimensional, one of the most frequent things is like these KD trees that Sanjoy mentioned. In high dimension, it's usually LSH, right? So that's roughly speaking the split between these references. All right, so in KD, this is like KD trees, right? This is how you split the space when you pre-process the point. And this is how you execute the query. When you have the query, you're basically searching them among these partitions. So it's kind of like going through a binary tree or traversing one path in a binary tree. Okay, so we're going to talk about high dimensional spaces. And a very useful tool here is the dimensionality reduction, or the Johnson-Lindenstrauss lemma, which says that you can reduce the dimension significantly. And it's being used somewhat similarly to these KD trees. Okay, so now what I want to talk about today is really, this is like just the background. I want to talk about some data-aware partitions. So as opposed to this Johnson-Lindenstrauss just projects in a random direction in high-dimensional cases, there are some works that actually look at the data points that you have, and then choose the direction to project, not uniformly from the sphere, which was also mentioned in Sanjoy's talk about this split trees, not split trees, split trees. So the direction there was uniformly from the, say, unit sphere. Here, in many, what I'm going to talk about is where the direction is chosen not uniformly, but actually using the data points that you have to bias the directions. Okay, and in general, you want to say maybe this can optimize, improve the result, because now it's optimized to the input, to the data. Okay, so maybe if the points lie on kind of something look like lying on along generally like this line, this direction, then maybe the direction you want to project is not just random from the sphere, but along this direction or something very close to it, and this will give you the most information. Okay, and then after you do that, maybe you repeat on each subset of the points in some way. Like for example, here, after you project the points on this, let me go back. If you project on the first line, then you split right to left, like in KD trees that Sanjoy mentioned, and I skipped in my slides. So you have 50% of the points here, 50% of the points here. Then you do it recursively on each one, a similar computation. Okay, then it's going to be a somewhat similar algorithm. Now, the question is how to choose this direction. By what I described before was really using the signal in the data, using kind of like the most significant direction, which is basically like the directions determined by SVD or PCA. You can pick your favorite acronym here. So there's been a lot of work on this, and these are like some partial list of references and how to do this, right? You choose this direction that I said in the beginning using PCA or SVD, and then you split the points maybe into two, or maybe you optimize it somewhat differently, and then you do recursively on each, say, half the points. Okay, but so it's somewhat similar to KD trees, except that the split is not according to the original KD tree is according to the standard basis. The split tree is according to a random direction, and here it's according to, say, the top direction from the PCA, top singular vector. Okay, and now it's data aware because the direction depends on the data. So the entire data structure depends highly is optimized for the data. Okay, now in practice, all these papers that are more empirical, they show a very good performance, and they claim to outperform, say, LSH or these kind of methods, which are known to be like almost optimal theoretically. On the other hand, there's no proof that this method works, right? This is like empirically, they're very successful. They give a lot of high accuracy using fast running time, small storage, and these kind of things. So people usually use them, and we want to understand why. Okay, even though we know that Johnson-Lindenstrauss result on this dimension reduction are optimal. Okay, so is there like a way to understand this non-worst case scenario? Maybe. So I'm going to suggest a specific model and then talk about two algorithms that are different but somehow follow the same outline that I mentioned here with this PCA, using the PCA directions. And we were able to analyze both of them mathematically to say give like accuracy guarantees because we have this specific model I'm going to tell you about. Okay, so what is the model? It's like a probabilistic model or maybe half probabilistic, half worst case. So in general, I want to have like a low dimensional signal with a large noise. Okay, so it's all sitting in a very high dimensional space. But let's suppose what I call it here the signal is that there's some subspace. So all the points come from a subspace U, where U stands for hidden or unknown. Okay, so there's a unknown subspace which is low dimensional. Okay, of dimension k, which is much smaller than d. Okay, so this hidden subspace. Think about like a 3-dimensional subspace, or maybe 2-dimensional subspace, maybe even 1-dimensional subspace inside a huge high-dimensional space. And all your points come from this hidden subspace. Okay, so in a sense, you think you're working with a low-dimensional problem, but you just don't see it. Of course, if you're giving the points in this way, you are able to see it, but in a second you won't. But yeah.
So this is only considering linear subspaces. It doesn't consider manifolds.
Yes, right. This is a linear subspace. But you don't see the linear subspace, okay? It's like hidden here. And then your actual data, so this is like the signal, the true signal, but it's perturbed by some noise. So the data is really, each point in this subspace is perturbed by a full dimensional Gaussian noise. So the perturbation takes it out of this subspace. Okay, and then the noise is really large, as you're going to see in a minute. Okay, so this is really difficult to identify the subspace. Okay, so this is like a one-dimensional case. The points are supposed to be exactly on this thing, and now you move them away, and it's a huge noise, so kind of like they look like they're all around. Okay. Okay. So to formulate it a little bit, I'm going to take the matrix P. So I don't remember. Maybe the columns are the data points, and you just add IID Gaussians, right? So it doesn't matter if it's the columns or the rows, and you get a new matrix P tilde. Okay. And so P is the unperturbed, P tilde is the perturbed data. And what you see in the algorithm is only the perturbed data, of course. Now I'm going to assume that each point has at least unit norm, so the signal there is a signal. It's not going to 0. That's kind of like a normalization. We're going to assume it's for every point. And now you get a query point. I'm going to choose the query point in a specific way that it's like very close to one of the points. Okay, so it's like a kind of like there is the correct answer that you want to answer, that is you're supposed to answer. So the query is not arbitrary. It's very close to one of the points, or relatively close to one of the points. Okay, and it's going to be like a unique nearest neighbor. Okay, so what this point, so again, you take this query point and you also perturb it by a Gaussian. So what you really get a query is Q tilde, but this is not very important. The difference here is not, I mean, when you go to the math, it's not that important. The question is how close is Q to the true data point, the closest one. So there is a P star, there is a point P star, which is the closest one, which is within distance 1. That's like the right nearest neighbor. And we're going to assume that for everybody else, the distance is at least 1 plus epsilon.
So P star and P are in P tilde or in P?
No. If there's no tilde, then it's in P. I try to be very consistent. I hope I didn't make a mistake, but okay. Then you perturb everything. You perturb the points P and you perturb Q, right? But like the initial question.
So you lose this uniqueness completely, probably.
That's a good question. So it depends on the amount of noise. I said the noise is huge, but it's huge. You'll see in a minute. But it's still so that the exact nearest neighbor remains the same. Okay, this requires calculation. I mean, it depends on how large it is. This is pretty large. So I'm going to talk here about the dependence mostly on D. Okay, so this sigma, right? This is like the Gaussian standard deviation in every direction. It's going to be like 1 over D to the 1/4. You'll see in a minute why. I'm going to ignore dependence on epsilon, k, and log n. Okay, there are also like, you have to be like smaller by something like k, log n, and smaller by epsilon or 1 over epsilon. So I'm going to ignore these terms. Okay, so think of it this way. Okay, so does it work? Yeah, okay, so what happens, the noise is large. What is the magnitude of the noise? Well, it's basically a sigma in every direction. So you sum up, it's going to be sigma times square root d. That's the magnitude of the perturbation. And by my choice, it's about d to the 1/4, which is bigger than 1. Okay, much bigger. I'm thinking of like epsilon maybe is like 0.1, and all these are like small constants, kind of, but this is large. Okay, so the noise, the amount of perturbation actually is much bigger than the initial distance that you start with 1. Okay. However, you can still prove that the exact nearest neighbor is the same. In this case, it happens because kind of like all of the perturbations are very close to the expected perturbation. It's highly concentrated. And that's kind of like the deviation in this distance. And they're all going in which direction? Well, kind of orthogonal to the k-space, k-dimensional space. Right? So they all go like contribute the same for all the points and so on. So they contribute the same amount. And that's what answers your question. So here what happens in this model, because there's so much noise, the top k dimensions of this P tilde, if you're trying to do SVD, and you look at the top k subspace, right, of this PCA, of this P tilde, it's going to get they're going to get subconstant mass, because just the noise is so large. Basically, it affects the top k subspace, and therefore, like all directions look almost the same or something. And it's, as opposed to having like in P, where if you start with P without the Gaussians, then you'll have like k positive singular values, and then everything else is 0. So this would not work. And Johnson answer would not work either, because after the perturbation, the distances are still the closest one. The one that you start P star is still the closest one, but the gap has narrowed by so much, right? I mean, both the closest and the second closest points are in the same order, but the values are now very close. Kind of like you added like a huge quantity to both of them, right? To this one, it's going to be like 1 plus this this noise, right? In both of them, and one is going to be, the second one is going to be plus some epsilon. So it's going to be very indistinguishable for Johnson and Strauss kind of projections. Okay, so what algorithm would you like to do? You're still going to want to use PCA. So how do you want to find this subspace, unknown subspace U? Okay, of course, the natural thing is like try to compute the top k subspace U and solve the nearest neighbor search problem there, right? Because if you compute the top k subspace, intuitively you want to get this subspace U as your solution. You project all the points to there because you want to cancel out the noise. And then once you're inside k-dimensional subspace, you can do the computation quickly because k is small. Okay. So This would be done if this PCA exactly recovered. So I'm going to use the letter S for this what the algorithm gives us, which is the subspace, the top k-dimensional subspace S. Ideally, it's going to be U. But because of the noise and stuff, it's not going to be exactly U. Okay, so if it were U, then it would be done with this approach. Okay, so is it true that we can do such a thing, like somehow reduce the problem to a k-dimensional subspace, get rid of the noise, and then use whatever algorithm is known for k dimensions? This is basically the best we can hope for in this model, because we started with a worst-case k-dimensional scenario. Right? In this k-dimension, the subspace U, I didn't put any assumptions. The point need not be uniformly distributed on this in this subspace U. So that's the best we can hope for. And effectively, we want to reduce the dimension D to K. And the spoiler for what we're going to see is the answer is yes, we can do this. Okay, so we're not going to, as I said, we're not going to find exactly U. That's going to be a problem. The problem is that out of these K important directions in this subspace U, this unknown subspace U, let's think of that like maybe half of them are really strong and half are really weak. Okay, like, I don't know, endpoints going like this, use these K over 2 directions, and square root endpoints use another K over 2 directions, uniformly or whatever. Square root endpoints are going to give you much less contribution to this SVD than the endpoints. Right? The total is basically endpoints. So you're not going to see them, and then they're going to be overtaken by the noise. The noise is going to give something already bigger. Okay, so here is like an illustration. Suppose these are like the 2 important directions. One direction, really a lot of points go in that direction. And there's one point like in the second direction. Now if you try to project, you're not going to see this the second direction. If this is case k equals 2. Right? So you run the algorithm, you find this direction, but the second direction that you find is some random direction. So you basically don't see this. And you're going to project on this, and now everything is going to be like a mess, because you're going to get spurious results. Okay, just because the being correct on half the directions intuitively is not enough being correct on all k directions. That's the point here. Okay, so here is the intuition for the first algorithm that we do. Well, the algorithm is going to be effective, but not for all the points. It's only going to be effective for a subset of the points. It's going to be a large subset, so that's good. We're going to make a lot of progress. And we have to identify which subset of the points we can do, it's going to succeed on. So we're going to call these like well-captured points. So which points are called, this is like intuitively at the moment, which points are well captured? Points where the signal is mostly inside the top PCA space of the algorithm. That should be the top PCA S. Okay, so if S is close to U, then I think that for many points, this what I'm going to find, so in this algorithm, and in this example, sorry, if we run the algorithm and we find 2 directions, which is this one and some random direction in space, then all these points will look that they're like the right place. But this one looks like unrelated. So you want to kind of ignore this point. We can identify this, right? Because in our computation, these points lie, in this case, inside the space. And that outlier lies outside the space S that we find. Okay. And the idea, one more thing about the high level, once we do that, if we can manage to, like, say, solve half the points here, then we're good. We're going to prepare a data structure for them, remove them from the data set. Now we have like another n over 2 points for which we don't know whether we have a good algorithm. We can just run the same algorithm recursively on n over 2 points and continue. So that's going to be like log n different data structures, and then we do it just iteratively. Okay, so here's more precisely what is this first algorithm, which is relatively simple. You find the top PCA. This is like the pre-processing, right? You find the top PCA subspace S. You find in this the set C, which are all the points that are really captured well by the subset, which your definition I'm going to give you in a minute. And then you build a near neighbor search data structure only on this set C. Okay, so that's, let's say, think of it like half the points or something. And you take the set C, but you project it on the subspace S, because basically you want to cancel the noise. Okay, now let's suppose you have a data structure on n over 2 of the points. What's going to happen with the other n over 2? Well, just take this other n over 2, repeat recursively, build a new data structure for them, again n over 4 and so on. So I'm going to have eventually, if this works like this, log n data structures for sizes n over 2, n over 4 and so on. So the overall size is fine. When I have a query, I'm just going to run it against each of these data structures. So they're going to be log n kind of like queries. That's a slowdown of factor log n in the runtime, and the space is fine, everything is fine. Okay? So it's enough to analyze basically one iteration in this sense. Yeah?
Somehow it depends, and if you want to do label prediction, it depends on whether the labels were determined before the Gaussian noise or after. Because you talk now about kind of that the labels are after the noise. You really care about the true nearest neighbor and not about the nearest neighbor before the noise.
Yes, I completely ignore here the issue of labels. I completely ignore the issue of accuracy of prediction. It's only about the runtime of the near neighbor search.
But I thought that the noise was such that the nearest neighbor stays the same.
Yeah, they stay the same. But I'm saying I don't talk about the accuracy of the label, but yeah. So yeah, sorry. So I want to make sure that this works. And the issue is that this set S that we find is not really you. It's only close to you in some limited way. Like I said before, like for intuition, think of like k over 2 of the direction that it finds, they're really coming from you, and k over 2 are just like random coming from the noise. Okay? So you have to figure out which are these k over 2, and also what does it mean to be close. Okay. So we start with like a simpler model where the noise is actually smaller, but then if it's so small, then it can be adversarial. Okay, so instead of being something like a perturbation which is very large, here the perturbation I'm assuming is like epsilon, which is, right? So it's like smaller than 0.1, whereas the true distance is about 1. So the perturbation can move the point, right? P tilde versus P, up to this alpha I, which is small but in arbitrary direction. Okay, so then I'm going to say that the point is called well captured. Okay, so I look at all the data points, all the P tilde that I have in the algorithm, and I compare them to the PCA space that I got. So if it's close, if it's within distance to alpha, right? Because just like in the picture I had before, the points that are on the exactly on inside the space or very close to the space say, oh, my space S that I found really spans that direction. It's good. And for some points, maybe I didn't find the right direction, so I'm not going to span. It's going to be like very far from the space. Okay, so this is the definition. The point that is close to what the algorithm finds. So I can during a pre-processing time, when I build the data structure, I can actually compute this and see which points are well captured and which points are not. And now there are two lemmas. They say, first, if the point is well captured, then the near neighbor search, this iteration will actually find it. Okay, if the query is, if this is the optimal point, P star, then this iteration of the nearest neighbor search will actually find this point. Okay, and it's just by triangle inequality here, because everything is moved a little bit, and like moved, I mean by moving the point back into the subspace S. It was perturbed, but then I move it back, but instead of into U, I move it back into S. That's the triangle inequality here that you use here. Okay, so if you look at what happens in S, it's very similar to what happened in U, and in U everything was fine. So up to these small errors, which are smaller than epsilon, this is fine. And then there's the second argument is that the number of iterations is logarithmic. This really needs to show that really the number of well-captured points is like half of something, or half or so of the points. Okay, and this happens because if you look at this total signal that you have, because every point has unit length, then like the Frobenius norm, or the total sum of squared lengths is something like n, and therefore it cannot be that all the points give you very little signal. Okay, this is the precise calculation, but yeah.
So do you actually have to construct this iteratively?
I don't know what I mean by actually, but that's the, yeah.
Of covering the whole points by these local coordinate systems, take the logarithmic number of them all at once.
To find them not iteratively, or you mean like after you find all of them, to build them into one data structure?
No, I just meant to find them non-iteratively.
This I think is going to be difficult.
Find some sort of local coordinate.
This I think is going to be difficult because it could be that, as I said, that think like n points use somehow half of the directions, k over 2 directions, and then root n points use another half of the directions. So totally you have like k direction, the entire signal is in k-dimensional space. But really most of the signal comes from k over 2 dimensions, right? they contribute a lot. The other ones contribute like root n compared to n. It's I mean, the total. And it's like overshadowed by the noise, which is like large per point because of all the other points noise. So really, the noise is going to be so large that this root n point is just like not enough. Like on average, they contribute like very little signal in that direction that you're looking for. If what you're going to do here, basically, if you follow this recipe, you basically remove all these endpoints, the first endpoints. Now you're looking only at these root endpoints that remain. All of a sudden, you have like this a very clear signal where they're going, compared to the noise in them, right? Because now you don't have the other points. So you have the signal in these points and the noise in these points. Now it's comparable. You see what I'm saying? Initially, you have like the noise coming from endpoints, and that's too large compared to this secondary signal. Yeah.
Maybe you could weight the points. If you could weigh the points appropriately, those square root endpoints would be more weight, and maybe you could sort of to make Yuval's algorithm.
Yeah, you can try to do like maybe. I mean, I have not thought about like something like multiplicative weights, and then still would take you like log n iterations. Okay. And I still don't see what's the advantage versus removing them, because effectively it's like smooth, right? Like soft removal. Right? I mean, might have other benefits, but just for this. Might get you away from these very strict assumptions. All right, so now I'm going to move to what I said is like the noise is really random and then it's large. Okay, but then we have to use the fact that this noise is really random. It's like highly concentrated, or it has like averaging properties, because you have a lot of perturbations, not just for one vector, for one point. So we're going to use this, here's like the basic argument in like few lines. Think of it like as a matrix, right? Of columns are the data points. So you have P tilde is P plus G, as we said. G is just a matrix of Gaussians. What can you say about the singular values? Well, if you look just on G, then you have a bound on the singular values. This is well known for random matrix theory, right? So here, remember that, I mean, lambda is like the maximum singular value, because sigma is the standard deviation of the perturbation. Okay, so you can bound them by something like n over root d, okay, for the singular values. On the other hand, if you look at P, then the rank is K here, right? And each one has direction at least one, magnitude at least 1. Okay, so you get that at least one direction should be at least n over K, because the Frobenius norm, the sum of squared length is at least n, and this corresponds to the sum of squared singular values, right? So here, if it's at least n, and there are only k of non-zero singular values, at least one singular value must contribute like n over k, in one squared. Okay? Maybe all of them, maybe only one of them. That's exactly the issue that you don't know a priori. It could be that only one of them is like that large, and it could be that all k of them, either evenly spread or not. This is exactly the point where it shows how important they are in the singular values. I mean, this shows in the analysis, because that's for the hidden point set. But that's a very important quantity. So basically what we're going to say, well, we're going to look only at directions that pass this. Think of it as a threshold. You put here like 1 over 10 times this, and this is the threshold. We're only going to look at directions that pass this threshold and ignore things that are smaller. Okay, this threshold is high enough that the random directions will not. So when you sum up these things, then the singular values can add up or cancel, can add up with positive and negative signs. So the large direction will remain large, but they can be not affected too much by this quantity, because this is small. This is like where we set the parameters. And those that are small, I cannot say anything about them. I mean, because it said only few of them, maybe only few of them are at least n over k. The ones that are smaller than the threshold, I'm not going to handle them now. They're going to be handled by the next iterations, basically. Okay, so now there's the other technical aspect that we need to deal with, is what does it mean for subspace S to be close to the subspace U? Okay, and actually, okay, so I think I didn't say it explicitly. The subspace S that we're going to choose in the algorithm is really only the PCA directions or singular values that are past this threshold. So of course, there can be at most k of them, because they sum up to at most something like n, but I don't know a priori what number. It's basically based on a threshold, not based on a priori choosing k top directions. Okay, so now I'm going to compare this S and U. U, we said, has dimension k. S, what the algorithm computes, the dimension at most k. So how do you compare these things? Turns out the top singular value is well known that it's not really stable under perturbations, because you have like the top, say, eigenvector. There's a tie between two values. One you perturb, one of them is going to be larger, and whichever you guess to be the right one, you're going to be very wrong. But it is stable if the second singular value is separated, is much smaller than the first one. And it's going to happen in this case, not for the first and the second, but because of this noise magnitude is much smaller. So we still have to define what does it mean. So we have some sort of stability, approximate some stability, but what does it mean to be close? And here we're going to use a theorem that is called the Weizmann's sine theta theorem. Okay, so this was studied, and it's basically this quantity. I have a picture here, so you'll see in a minute. Okay, it's a measure of proximity between the subspaces S and U. In this case, it's called sine theta of this thing. There's this quantity, and let me tell you what it is by a picture. Okay, you have this subspace U. Okay, and now your algorithm computed this subspace S. Is S close to U? Okay, you take any point in S, the worst point, the maximum point that's here, right? And you see what's the closest point in U. And if there is somebody in U that is close, that means that S is close to U. So in this case, S could be a smaller dimensional subspace than U. Of course, if it's bigger dimensional, somebody is going to be far away, so it doesn't make sense. But if it's smaller dimension, that's fine. And if it means that you take some subset of directions, think of it this way. If you start with U, you take a subset of these directions, you move it only by some epsilon, and this quantity is going to be bounded by epsilon. Yeah. All right, so this is the way we measure things. And it's not symmetric, right, because of this definition. This is from S to U and not the other way around. Okay, and this theorem, was developed by Davis and Kahn, and then by Weizmann. I think Davis and Kahn was for symmetric matrices, and Weizmann's theorem is for general matrices. So it shows something like this. If you start with a matrix, just like this perturbation theorem, if you start with a matrix P and then you perturb it, right? You take P and then you perturb it, you get P tilde. The question is, if you look at the top subspace of P and the top subspace of P tilde, are they close? If it's a small perturbation, they should be close. So they actually developed this to say, in what sense are they close? Right? This definition is like the right definition to measure the proximity. And they also give bounds, like with high probability, I guess, is missing here. And they don't have to be of the same cardinality, the subspaces, and so on. And it largely depends on the operator norm of G, of the Gaussians. Okay, actually it doesn't have to be Gaussian, any matrix. But of course, if it's Gaussian, then you know that this operator norm is small. Okay, so this bounds like what happens to this, why the vector S is going to be in this particular way, particular sense, it's close to U. Okay, so this is good enough because if you remember what I said, well captured was really about distances. If you're close to U, if the point was close to U or something, that's really about the right thing, which I don't have time to go into the details. But this really captures the right thing. This is the distance between S and U. That has to be verified. I didn't show it here. Here are like two minor but important issues to complete the analysis. One is if you do it iteratively, okay, the first iteration we said is this model and stuff like that. Well, just like in Sanjoy's talk, the second iteration, now the data is not random. It's affected by the choices of the first iteration and so on. So how do you analyze those? Now it's like a mess to analyze. Here is like a simple fix. Instead of computing the PCA as I said, you pick something like log n points, or k log n points, so you have like log n per direction, and you compute the PCA for these points. Okay, so it's going to be and you have to prove that it's a good approximation for the PCA of the original data set. So now for these points, you cannot use them anymore, so you can just compare the query against them like naively. That's the only log n points, that's fine. And now the next iteration does not depend on what your choices in the first iteration. Okay, now maybe that's not needed. We don't know how to remove this from the analysis, but maybe you want to use it anyway. I mean, in practice, which we didn't try. I haven't seen people reporting that they did this. Maybe they do it for speed up, though. Okay, so eventually what we can prove about this model is that the number of iterations is something like square root d log n. And in each one, we have this subspace S, which has dimension at most k. So we're going to run arbitrary, whatever your favorite algorithm for k dimensions. And that's why you get this runtime, which is something like 1 over epsilon to the k, and these dependencies on log n. Okay, so basically, we reduce it to a few instances of k-dimensional near-neighbor search. Okay, so the second algorithm, and this is going to be like very vague very short on details. It's another algorithm which we analyze in the same paper. This is even closer to the algorithms used in practice. The algorithm we suggested is not really the kind of thing people use in practice. It uses this idea of using the PCA directions, but it's something that we came up with based on this. This is similar to the algorithm that people have used it's called PCA tree. And this is basically like in this picture, you find the top one. Even though you think of like these k-dimensional spaces, you find one, the top direction, the PCA direction. You project onto that direction. Now you partition the points into slabs, right? So after you project around the line, basically cut it into intervals, or if you think in the original space is like slabs. Okay, so now the points are partitioned into these sets. Okay, and then you repeat recursively on each subset. Okay, recursively you do this top PCA direction and so on. Okay, that's the algorithm. Okay, but except that when you search, you don't search only the right slab, you also search, say, the preceding and succeeding slabs. Okay, so you have some in the search, you actually spend a little bit more time when you expand this thing. Okay, so this is the algorithm. We are actually able to analyze it, and it gives like nice results in this model, right? For this adversarial plus probabilistic noise model, it actually works very well with all these with a certain careful analysis. Some points that you have to worry about is that you have to center the points, because after you move the points on the slab, they're going to be like far away in some slab, so they're kind of like shifted. You want to kind of like center them back to the origin, so that kind of like the noise is like goes in all directions equally. So that's a technical issue. And another technical issue is that the points may accumulate in some parts of the tree because we started with adversarial data set. So you have to be concerned about these things. Otherwise, it doesn't work. So this is kind of like modifications to the algorithm. And I said that we start with the algorithm that people use in practice, right, with this PCA. So you have to modify it accordingly. This centering, for example. Okay. So overall, what happens is that if you do this tree, kind of PCA tree, the number of iterations or the depth of the tree is only 2k, because that affects the runtime and everything. And 2k is like the right dimension. And then you stop, okay? And then you look at all the points that you reach there. So basically, the performance of this algorithm is like analogous to what happens in dimension k log k. Okay, so it's really, you didn't reduce it to a k dimension, you reduce it to a kind of like a k log k dimension problem in terms of NNS, in terms of runtime. This is because you have a k to the k instead of like only epsilon, 1 over epsilon to the k. Okay, so we managed to do this kind of dimension reduction, but just for this setting, not general dimension reduction. Let me just point out that after this work, there's some other algorithms that look at data-aware analysis, so we depend on the data points. In this case, it's 4 worst-case algorithms. It was done by 2-3 papers by Andoni Rasenstein and a few others and co-authors. I mean, this is one of the papers, the tight result. And here we didn't look at worst case, we looked at low-dimensional plus noise. Okay, and we showed that it actually using PCA is really effective on these kind of models. So hopefully it can explain when to use it or why is it effective. Is it effective? And I think in general that's a good question, right? To explain somehow empirical success in the sense that next time if I wanted, well, possibly somebody else, it's more likely, wanted to actually execute an algorithm, they will know which algorithm to choose for the data they have in hand at hand. Thanks. Yeah. So
let me suggest an algorithm, which I'm sure you thought about. Tell me why it doesn't work. First, you cluster the points, and I don't know how many clusters you need. And I mean, any old clustering method, maybe just iteratively remove nearest neighbor balls from and then replace each ball with the average, and then do PCA on that. So by taking the average, you're reducing the Gaussian noise. And by taking clusters, you make sure that the different averages capture different parts of the space, so you're not.
I have not thought about it. I think initially I wanted to understand when PCA would work. So right, it's not like we tried crazy algorithm. No, we didn't try crazy algorithm for this model. Okay, I mean, so I'm not sure we thought about it.
If you capture the k-dimensional subspace, then the problem becomes easy.
Yeah,
right?
yeah.
So if there's a way to go there.
Well, it becomes easy if you find it exactly. If you find it approximately, then you have to get a bound, as like I discussed with these weddings as sine theta theorem. So the question is like also an issue of accuracy, and you find like a subspace of some lower dimension. You have to find the right dimension. We had this threshold. So you find the right dimension that is effective. So it's not that simple. But going back to your first sentence, I think the clustering will not work very well because the noise is so large. Basically, you're not going to see anything.
By averaging, you're reducing the noise.
But you have to do the clustering first. If you do the averaging of everything.
No. But I'm taking, right? If we take average of points that are on the subspace and each one had an independent Gaussian, then the sum is also on the subspace with a Gaussian with a smaller.
Okay, so let's suppose I take the original data set and it's symmetric. For every point P, you have minus P.
Okay, but that's why I cluster. So that P and minus P will not be in the same. So I try to catch all the regions.
Yeah, so in that sense, I think the clustering will not work well because the noise is much bigger than this signal, which is 1 unit, and the noise is like d to the 1/4.
But is the noise much bigger than, say, the...
Not if you know the right direction. If you know the right direction, you look only in this direction, the noise looks small because it's only sigma.
Yeah.
But if you don't know what is the right direction, look just like in JL, right? You look at all directions, then it looks like sigma times rho d, which is like huge.
But the clustering itself should...
But clustering, there is a linear model underlying here. And clustering doesn't take this into account at all.
Mm-hmm.
So you're losing the main assumption if you do just blind clustering.
Yeah, because the clustering is, let's suppose it's done by Euclidean distances, like proximity, sum of Euclidean or sum of squares or something like this. Then this linear assumption is going to be hidden by the noise because the noise is much bigger.
What if you take this
I
labs
thought
that you
what you
showed
meant
for
was
clusters?
to have
It's going to be good if you know the subspace.
No, but you
just partition it into balls, right? Cover the data set by balls of equal radius. That's what I understood the clustering to be. Not sum of squares or anything like that.
Yeah, iteratively remove nearest neighbor ball. Because you said the nearest neighbors are preserved by this noise, right? It's not big enough so that you don't have nearest.
Yeah, but it's very strict, right? Instead of the gap being 1 plus epsilon, it's going to be like d to the 1/4 and d to the 1/4 plus epsilon. So, right? I mean, it's additive. You add to the same quantity to both distances. But instead of being 1 and 1 plus epsilon, which is like also multiplicatively distinguishable, you add a huge quantity. So now they have the same order. One is bigger than the other, but they're almost like the same quantity. But I have not thought about this algorithm, so yeah.
So perhaps it's one of your questions too, but can you hope for a deterministic condition on the noise, like the operator norm being bounded, under which this algorithm works?
Operator norm of what?
The noise matrix, just the...
So I think in principle, as you saw in the slides, now the question is, how much things are being used in the proof. I think that should be enough. However, the algorithm works in iterations. So the second iteration works on a subset of size, let's say n/2. Now it depends on the same assumption on that set, right? So it's not going to be that simple, but maybe you can refine it in this sense, right? That and I'm not sure how to define it because you have this arbitrary subset of size n/2, n/4, and so on.
Okay, thank you.